pleasure to introduce the next speaker, Brady, who will be talking about, well, Linfinity comorphisms. Not sure what.
Yeah, cool. So as I said, hello, and yeah, thanks for having me on Mackenzie Day in particular. Seems very weird because I mean, 2 years ago, I was taking like a vector bundles course taught by him, so it's all very strange. But yeah, so today I want to talk about Linfinity comorphisms, and this kind of direction of work is basically looking to generalize a kind of program of Kirill's, the one that sort of started with the Higgins-McKenzie paper of 1993, about a bunch of relationships between Possum and Lie geometry, with comorphisms being considered in particular. And we want to extend all of this stuff to the kind of higher bracket world. So, I mean, first off, like what we can talk about is, I mean, I'm mainly going to be thinking about vector bundles rather than fiber bundles, but we can define it in full generality, so why not? So, I mean, if we've got fiber bundles, then we can define, you know, just an ordinary morphism of fiber bundles as a pair of maps where we have these kind of two maps. So this is a smooth map, and this is another map that's going into the pullback, and they're going in the same direction. So this is kind of equivalent data because you can always factor through pullbacks. So there's a kind of dual notion, which is that of the comorphism. And yeah, so here we don't have a map of sections. We just have sections related by a map. But we can kind of flip the picture around. So now we have a kind of a smooth map going the other way and a map from the pullback bundle. And so this does induce a map of sections, which is kind of more useful for certain purposes that we might be interested in. So yeah, we get this map of sections, but we lose a map of total spaces, which makes sort of some other things more complicated. So the kind of like canonical example is if you have a smooth map of manifolds, you obviously have the tangent map over that, but then you also have the cotangent comorphism, which is basically once you factor through the pullback bundle, you kind of like flip some of the arrows on the top around by dualizing, and then that's kind of like your very stereotypical comorphism. Okay, so now let's suppose that we have Lie algebroids, so A and B, and yeah, in 1993, Higgins and McKenzie introduced this idea of a Lie algebroid comorphism. So what they want is that, I mean, I haven't specified that comorphisms need to be fiberwise linear, but in their case they are. And they also want a kind of natural condition on this map of sections, where it just relates to brackets. And we also want a kind of this condition on the anchors. And then so their relationship with Poisson structure, so just to clear things up, by a Poisson bundle, we basically mean a vector bundle where we have like, it's a Poisson manifold, has Poisson structure on the functions on the total space, but in a way that preserves the kind of bundle structure, i.e. the brackets preserve fiberwise linear functions. And so they showed that these kind of things are basically each other in disguise. Lie algebroid comorphisms going one way and fiberwise linear Poisson maps of Poisson bundles going the other way are in one-to-one correspondence. Okay, and so that's the kind of result that we want to bring to the strongly homotopy setting. So what we'll say a Q bundle is a fiber bundle just with a homological vector field. So it's basically just a Q manifold structure on a fiber bundle. So if we're thinking of our fiber bundle as being a vector bundle, then the parity dual of this space will be an Linfinity algebroid. So we have a kind of whole sequence of higher brackets, which give the space of sections an Linfinity algebra structure in the anti-symmetric convention. And we have all these higher anchors, and the higher anchors assemble into an Linfinity morphism. And we have a kind of a whole bunch of Leibniz type identities. So if we want to multiply one of the sections inside a bracket by a smooth function, we can pull that outside with a Leibniz type identity involving the anchors. And then a P-infinity algebra, we basically say is going to be an anti-symmetric, the same as before, L-infinity algebra, where we have a whole bunch of multi-derivation, all of our different brackets act as multi-derivations on the multiplication that our algebra already has. So, and then yeah, P-infinity manifold is just a manifold that has this structure on functions. And just like before, a P-infinity bundle has this structure, and then also all the brackets preserve the fiberwise linear functions again. And then we also have this other kind of parallel notion where S infinity is this kind of like homotopes Houghton thing, where in that case, what we'll have is a symmetric L infinity algebra structure on functions, and the brackets will be different parities and that kind of thing. But they're kind of quite similar. So this means that we have these 4 different kind of manifestations of the same structure on all these different neighbor bundles. So we can take our original bundle, we can dualize, and we can parity reverse, and this gives us all these different neighbors. And then basically all of these different structures manifest in these different ways. But they're kind of, we can see all the relationships between them quite clearly. And that's on the level of objects. So then we just ask about what about maps between these objects. Okay, so the definition I want to present is that if we have a comorphism of Q bundles, then we'll call it a Q comorphism if it induces a homological vector field on the pullback, which makes this diagram commute. Which looks kind of strange, but you can formulate Lie algebroid comorphisms in a similar way once you pass to the duals, to the parity reverse things by Weintraub's theorem and such. And if we have vector bundles specifically, then Q comorphisms reduce to Lie algebroid comorphisms if our homological vector fields are of the correct weights, and our comorphism is linear, like I said. And we also get L infinity maps of L infinity algebroids if our bases are the same and we're not doing any kind of base mapping stuff. Okay, so we want these things to kind of behave in ways that we would expect. And so we had that kind of Higgins-McKenzie definition in mind where we had that the brackets are related by a map of sections. And then we had that condition on the anchors. So we should want that to be true in this case. And with that definition, this is, so we do get an induced map of sections. And then we also have a nice condition on the anchors that also, in fact, looks exactly the same. But now these 2 anchors and this map of sections are now not linear maps, but they're L infinity morphisms. But everything works kind of very similarly. Okay, and this also gives us a way to define actions, which is kind of like, this definition is a very sort of broad, subsuming definition of what an action of a Q bundle on a manifold could be. All we want is that it's just an L infinity, well, I guess a Q comorphism from the bundle to the antitangent bundle of the manifold. And that will give us a kind of transformation from sections of our bundle to vector fields, which will act on this manifold. And so, yeah, like with this kind of setup, because this antitangent bundle is just a Lie algebroid with the Durand differential, is a Q bundle even. So this generalizes ordinary kind of actions of Lie algebras and algebroids. And then this, I mean, a specific example is there's the kind of L infinity adjoint action that's in this triangle Lazarev paper. And this is also an example of this definition. Okay, so we've kind of talked about what comorphisms should be, and now we just need to talk about what the appropriate notion of maps for P infinity bundles should be. So this means we need to go into kind of Thickmorphism territory, because as Ted was talking about, we need our pullbacks of functions to be L infinity morphisms. So we can't have linear pullbacks. So we need these kind of generalized maps. So we have 2 kind of different versions. So an even Thickmorphism is basically, you can think of it as a kind of like a submanifold specified by a generating function in the cotangent bundles, and an odd Thickmorphism has a generating function of the opposite parity, and it lives as a kind of submanifold in the anti-cotangent bundles. And all of this is formal. So both of these contain the information of just a carrier map. So every Thickmorphism kind of includes within its information an ordinary smooth map, but it's got some other stuff going on as well. So the brackets on a P infinity bundle are introduced by master Hamiltonians, as we saw earlier. So these are even formal functions on the anti-cotangent bundle. And we kind of get our end brackets by using derived brackets with the ordinary Southern bracket and this master Hamiltonian. So how these are related is we get a way to define the kind of appropriate notion of Poisson map for this P infinity setting. So yeah, if we have an odd Thickmorphism from one P infinity manifold to another, And it satisfies this condition where in fact it should also be a star here. So what this means is that this is the projections from this kind of like a product anti-cotangent bundle to the individual components. What we want to do is pull these Hamiltonians back up onto the products, and they should agree on the products, at least on the actual sort of submanifold specified by the Thickmorphism. So if all of that is satisfied, then we say that it's a P-infinity Thickmorphism. And this is our correct notion of map for P-infinity bundles. So what we have in terms of relating these maps is that if we have our vector bundles living over the same base, then what we can do is use Thickmorphisms to form like a joint or dual maps of any kind of level of, well, any map. It doesn't have to be linear. So if we start with an ordinary nonlinear but fiberwise map over the same base, then this has a thicker joint, or I guess thicker anti-adjoint, because there are kind of even and odd versions for this, but we'll talk about this one. And this notion of the thicker joint coincides with the ordinary adjoint if we start with a linear map to begin with. So if we have two L-infinity algebroids, then the duals are going to be P-infinity bundles. And if we have an L-infinity map from one to the other, then the thicker joint will be a P-infinity Thickmorphism. And you can reverse this in certain cases, but not every Thickmorphism dualizes to an ordinary map. So that's the kind of where we were up to. And then we wanted to extend this to kind of maps that are over different bases. So if we have two L-infinity algebroids and we have a comorphism, so specifically nonlinear, then basically you can continue this correspondence. So if we have a Q comorphism of L-infinity algebroids, then there is an induced fiberwise P-infinity Thickmorphism that lives over our base map. And then again, we could have done a similar thing for S-infinity instead of P-infinity. And we can kind of reverse this process, like I said, in the cases where your dual of your Thickmorphism will actually be an ordinary map. Otherwise, you would kind of need a notion of what a thick L-infinity comorphism would be, which is not something that we've investigated yet, at least. So we've shown this for a certain family, and it should hold for slightly more than we suspect. And then, so kind of another result of McKenzies that we were kind of looking at was this, the kind of basis for McKenzies cotangent philosophy, which is whenever you have a Poisson map of Poisson manifolds, then you have a Lie algebroid comorphism of the cotangent bundles. And working with this cotangent picture often provides like a lot more insight into Poisson geometry and McKenzies' view. So yeah, exactly. So what we want to do is generalize this theorem to the higher bracket world. And so what we want to do is start with a P-infinity Thickmorphism of P-infinity manifolds. And then if we form its antitangent, then this turns out to be, this Thickmorphism is fibered over an ordinary map, which is kind of surprising. So it seems possible that this should dualize to be an L-infinity comorphism. And unfortunately, I didn't manage to get this done quite in time, which would have been really nice. But I believe it should be in this larger family of dualizable P-infinity or S-infinity Thickmorphisms. So we should have this L-infinity comorphism, and I suspect we will do very soon. Okay, yeah, I'll call it a day there. Cool. Thank you much.
Any questions, comments? May I ask what is the larger family referring to?
So there are certain Thickmorphisms fibered over smooth maps, which are kind of obviously fibered over smooth maps.